Hello. So I feel like I've finally gotten my client server um, set up a little bit better than it has used to been. Um, and I just want to discuss the current architecture of it. So this is all in the context of a MWE, so minimal working example, and it's going to be the minimal working example networked FPS game, and it's also only going to be in the context of there only existing like one uh, non-local entity, so controlled externally, and one local entity, so that's like your player character. And the reason why I'm focusing on that is because that's a place that's understandable for most people, and extending it just means like more. It doesn't mean conceptually new things. Well, I'm not 100% sure on that yet. That will be yet to be seen, but for now, I'm happy with this, and I just want to explain the concepts behind how I got this to work. And additionally, this is also um, sub-tick movement. And so a tick means the tick rate of the server, and the tick rate of the server is um, at a rate which is like something like 60, and the client will be able to update their local state at a frequency higher than 60. So they can what usually like you'll select a frequency which is an integer multiple of 60. Um, and what that allows you to do is it allows you to match the highest refresh rate of your monitor so that like your movement will update on every single tick. And I'll explain how it's done. And also non-local entities are updated at this frequency as well. And that allows because the servers so subtick just allows you to update your local state faster than you receive game states from the server, and also we do entity interpolation, so that means we will update the non-local entities at faster than 60 hertz as well. Okay, so let's first talk about the local state and how we do that. So on the client, the main thing that happens is that first of all we have our main loop. Let's find that. Right. So inside of here, every tick we do something. So we set our uniforms, we update the state, and then we potentially send to the server. And I'll explain that in a sec. And also we draw and we do sounds. And the main thing to think about here is the state updating. So with this, the main thing to notice here is we have what's known as so everything relies on reconciliation. And so what that means is we allow the client to predict where you'll be, and then when you receive an authoritative client or an authoritative server state, you'll use that and reconcile against that. But the first part of that is processing. So with the reconciliation system, we have two things. So we have the state, and then we have the state update data. So what's a good way of thinking about this? So when you're updating your character, you have the inputs, um, so like what keys they're pressing and stuff, and then that produces a. So there's an initial state, and then when you apply a state update data, you get a new state. And that's fundamentally what allows us to do reconciliation is that we can like go back in time to an old state and then reapply state update data. I'm just going to call that a SUD, SUD, SUD update, state update data for short. So that's a SUD. Um, you can reapply your SUDs on top, and that allows you to rebuild the state when um, the authoritative server message comes in. So there's character camera update data, which is a type of SUD. It's just character. So this is for the camera, and so it will store the mouse position X, Y, plus the active sensitivity. And then there's character physics update data. And we have two reconciliation systems, one for like the camera and one for the physics state. And you could probably just do that all in one, but I like decoupling the two in case at any point I want to operate on the camera differently. But it could probably be one. And what happens is on each tick, so however fast your game is running, be it like 180, 240, 300, 360, and there's a reason why I'm talking in multiples of 60, but we'll get to that. We will apply the update. So that means we update the state instantly. We do that for the camera and the physics state. And that makes it feel live, i.e., when you move the mouse, your camera turns. So that's step one of this whole system, is that you update just like that, as fast as possible, pretty much. Now, let's think about that for a sec. Another component of this was that there was like a DT involved here, and I won't fully explain what this is yet, but like you're using a delta time in addition. So the physics update data is a delta time plus like where you're looking plus like your input state. You can see that here. So it's like DT client input state and then the forward vector of your camera. So that's the state update data, and I take that and I use that to update my position in space. Well, actually my velocity, and then I use the physics engine to update the position. But that is how the physics reconciliation works in terms of applying the update. Okay, so there's a little bit more going on here. So let's just keep scrolling down here. So that's shooting, and we'll get to shooting eventually, but we're not going to talk about shooting yet. So that's how we update our stuff. And we then send to the server, and when do we send to the server? Well, it has to do with these bundles, and the bundles won't make sense until you understand a kind of diagram here. So let me just bring up color paint. Okay, so you're gonna have the client and the server. So on the left, we're gonna have the client, and then we're gonna have the server on the right. And the client ticks very quickly with like arbitrary DTs. And the server ticks at a rate as well. And before you actually before you use subtick, the first kind of implementation is that like if you can't make this work, you can't make subtick work. So the first initial implementation is the client and the server both update at the same rate. So like client only does 60 and the server only updates its state at 60 hertz. And with this kind of update scheme, then what you have happen is so the state update data is like, the DT plus the input of the mouse. And specifically it's CPUD, which I just call like CPUD, which is like client physics update data. And if this is state 0, so like initial state, and this is like initial state 0, and then like the CPUD arrives like here, then we're still in state 0 hopefully. And then like we apply CPUD, I guess CPUD 0 here, and it will produce, yeah, it produces a state 1, and then over here it will process that CPUD and produce state 1 as well. And the whole point of it is that like whenever a new CPUD is created on the client, so CPUD 1, that will get to like the server, and then the server, because it's kind of like recursion. So the base case is that the initial states are the same between the both systems, and then if the initial state is the same and you process an identical CPUD, then on the next state these states like will match. And of course that's not actually what happens in real life most of the time, and it's all about how we can make it happen as closely as we can to that. And so yeah, one thing that's interesting is like, well, aren't both systems measuring their own DTs? So like if this is 60, you might get like 0.016, and then the DT on the client might have been, and actually, right, so the DT over here might have been 0.016, and then 7, and then over here, when it processed, like the CPUD, its DT comes from somewhere, and specifically its DT comes from like the measurement between the two, and so it could have been like 0.0165, right? And how do we like, so this is an interesting problem because this is client and this is server, and the server has to be authoritative, so the client can't be telling us like what the DT is because the server should be measuring that. And the way we can like fix this is, instead of like on the server using a measured delta, we use a perfect delta, which is like we always use like the value 1/60, even though that might not be how much time actually like has occurred. In my experience, as long as your system like accounts for the fact that it does this, and it's not just like blindly using 1/60, because if you use 1/60, then it's not like frame independent per se, because like, if it takes too long, if it takes longer or shorter, you're still getting the same value. So if like the computer runs faster, then it will appear as though like gravity will be running faster. And I find this is not actually the case if you do it correct. If you do it correctly, then you can get away with using perfect deltas pretty much. And I won't go into that specifically, like, but I can do that. What I'm saying is that I can do that, and everything is okay. And so that means that like both client and server can use these perfect deltas, which means even though the client sends over a CPUD with a delta time in it, I know that delta time will match like this delta time because it's using the same one, and that's like how you can get away with the fact that like the client shouldn't be able to tell the server how much time has elapsed, is that you just make it so that it always is the same between the two. And okay, sure. So that's how we could do the single one where it's like the same frequency on client and server. And when you're doing subtick, so when you have more than one tick allowed per like frequency on the server, how does that work, right? So the issue that we had before was that like the way we solved the issue before was that like the deltas could be equated because uh, both the client and the server ran at the same rate and we used perfect deltas. But now the client and the server don't run at the same rate. And so the way we get over this hurdle is that we use what I call a time bundled, a client update. What did I call this? Give me a sec here. Yeah, so client update data time bundle is what I think I called it. Yeah, client update data time bundle. And a client update data time bundle is a vector of ID tagged character update data, and character update data is just like the physics, the camera, and the firing data that was processed. So that's camera update data is like, or sorry, the character update data is one of those things that we talked about in the main function, where it's like we produce like the CCUD and the CPUD, and we use that with reconciliation to update our local state. We want to send both the camera and the physics, and also there's firing data, but we'll just say camera physics. We want to send that bundle over to the server so it can process it too. And sorry, I keep saying bundle, but I need to like specify what I mean there. So on the client, our processing happens at this level where it's like it's each granular tick is occurring, and we're using like whatever the CCUD or the CPUD is that we grabbed. We use that to get to the next state. And so what you get is you get a bundle of, so the collection of all of those CPUDs and CCUDs, and I'm just going to call them, so it's just CUD, like client update data, instead of specifying like each type. So it's CUD. So you have a collection of CUD here, and what you want to do is you still know about this like server tick rate. And so what you do is you bundle them, so you produce enough of these so that like the summation of all their delta times equals to the server's delta time. So like this whole time equals like that, the amount of time that would be processed here. And the way we also do this is that we still assume that the server uses perfect deltas, i.e. that this duration is like exactly 1/60, and we have what's known as like a time bundler, and this is where this will start making more sense. So the time bundler is trying to either fill out the current bundle or tell you to produce a new bundle, and you're either in the middle of a bundle or you're at like the boundary of a bundle. And what that will do is like you pass in the actual DT that is like being produced in the entire like processing loop, which is like how much time has passed. And so given that time, like let's say that time was actually like something like that, the time bundler will say, well, actually the bundle's going to end here, so scratch that extra time you had. We're just going to use like this much time for your CC or for your CPUD. We're only going to use this DT, and then like the extra is stored for the next bundle. And so what this allows you to do is it allows you to get this summation equal to exactly 1/60. And once you do this, the conceptual problem is solved, where now when you grab a bundle, so let's just say the bundle was like going from here to here, right? So the bundle consists of each CUD on each tick processed on the client. And this bundle can now be just thought of like the regular thing back when we just had the same frequency. So we just send this bundle over to the server, and the server will grab that and process each one really fast. So it'll do that one, that one, that one, all in one tick, right? It's going to process everything. And so if we call this the CUD bundle, so CB0, and this is like state 0, and this is state 0, and then it's also at state 0. On this tick, when CB0 is processed, so if this is state 1 on the client, and maybe I'll just write client up at the top, and then this is server state. And then so this is server 1 state. Then we can deduce that because S0 equals okay, I'll do this properly. So this is actually, let's just call that state 1, and this will be state 2 server. So these two are equivalent, hopefully, because like the way I like to think of that is like all the entities are like on the ground and nothing is moving. So these states are equal, and also the initial state of the client is equal to the initial state of the server. That should hopefully be the case. So that's equal to that, that's equal to that, and then to get from there to there, what is processed is CB0, right? Which is the CUD bundle 0. And so because so this shows you that like state 1 client is equal to state 2 server. So these two things are equal. And so that kind of allows us to understand how CUD bundles are kind of equivalent to just like sending over a singular CUD as we did when the client and the server ticked at the same rate. So functionally, once you understand how CUD bundles work and how you can do this, then you're good. It allows you to run subtick, and also the reconciliation system doesn't really have to change, because the only difference is that like the reconciliation is applying more states frequently, but like fundamentally it doesn't change anything about how it would work. So this allows you to make your client more responsive in that however fast you update, you can create more CUD bundles. But also just be aware that the more CUD bundles that are produced, the higher the network load, because a CUD bundle just keeps getting bigger. In the future, I'm gonna come up with ways to like make it smaller, but in general, you are packing more data, so it's no matter what, the network load is gonna increase. So this is what allows you to have subtick movement in the first place with reconciliation. Now what else? Okay, so a problem. So now we're just going to go back to some basics here. So client server, and oh yeah, something I did forget to say about the whole CUD bundle thing is that like you're still sending out at 60 hertz, which is like the send rate of the client equals the tick rate of the server. So you're not like sending out more frequently, but like the data you send out is just bigger. Okay. And with that out of the way, I'm going to talk about something that's important. So you have server on top and client on bottom, and they're both going to tick at the same rate. I guess maybe we'll just do this. I don't really want to do that just because there's like a phase offset in which they start, and so there's always a difference, but okay, so the bottom is the client and the top is the server. And what you need to keep in mind is the following idea. So under perfect, so assume these ticks are equally spaced both on the client and the server, and each time you send from client to server, it always lands here. So every server tick has a singular packet to process from the client. Now this is not the case. So I've talked about this previously, but there's variance in the time at which packets take to get to the server. So something that can happen is like if it so occurs that like your phase offset between the client and server was something like this, where it's landing right before the tick, then you could have something like this, and then this packet is a little slower than usual, and it lands here. And what happens is now you have what's known as an empty tick. The other thing can happen too, where you have your packets arriving right after the server tick, and then one of the ticks takes faster than usual, and now you have a double tick. And of course you can have, well, not of course, like you could have a triple tick or like double empties. It's just more rare for that to happen, and it depends on like how what the frequency is of each. But at 60 hertz, I find that you get double ticks and empty ticks most of the time. You can, if something really bad happens, you could get like a triple. But the main thing is like, the issue here is it's like a producer-consumer problem. So if on each tick the server wants to consume something, then there will be times when it cannot do that. And what that means is you'll have an empty tick. And the reason why an empty tick is not optimal is because empty ticks produce reconciliation error. So if you process the CUD bundle 0 here, then you process nothing here, and then you process CUD bundle 1 here. And on the client, what you did was you had CUD bundle 0 processed, CUD bundle 1 processed, CUD bundle 2 processed, CUD bundle 3 processed. Then because the server ticks no matter what, and it will update all physics entities, then let's do something like this. Let's say this is like the let's say this is a top-down view of your client's position. Then maybe on the client you go like this, yeah, and then like this. So after processing CUD bundle 0, you get to this position. After processing CUD bundle 1, you get here. After processing CUD bundle 2, you get here. And after processing CUD bundle 3, you get here. Now on the server, what will happen is you'll process CUD bundle 0, and you'll arrive here, which is the same. And then you'll have an empty tick. And because of the empty tick, you have to decide what to do, but in either case, you have to do something, because physics doesn't just stop running. So you might do that, reuse the previous like input state or whatever, and you'll extend out to here, and then you'll process CUD bundle 1, and then you'll be here, and then you'll process CUD bundle 2, and then you'll process CUD bundle 3. And so this is where reconciliation error comes from, is when the server has not had the same processing sequence as the client. We know that the CUD bundles are like once they're on the server, they're the same as they were on the client. So that's the only real cause of reconciliation error. And that's actually why you need reconciliation. Is there are ways to deal with this, which I will explain, but there's no like solution that will like solve it in all situations. Only in like nominal network conditions it will work. When stuff goes wrong, stuff will happen. So we want to avoid empty ticks pretty much, and we also want to avoid double ticks because if there's a double tick, you're not going to process both. Maybe you take the average of the two and process that, or maybe you just process the most recent one, but either way, you're also going to get error. So the only real way to really minimize error is to make sure that the processing sequence is almost identical on the client as it was on the server. So this is where a networked periodic signal quantizer comes in. And so yeah, that sounds complicated, but the idea is not that complicated. So what the and so a networked periodic signal quantizer, I'm just going to call it an NPSQ for short. So an NPSQ is something that makes it so when the server reaches out and grabs for a state, it will always be there. Well, there will be a higher probability of it being there. So before, what the system would do is it would just grab, and if like the network had variance, it could be empty. So this one way of fixing this is just like you hold an extra one, right? So you hold an extra state. So you delay on the server, but by delaying it means that like if there's nothing to grab, you have like a spare one to grab. And so the way you can think about this is that the server has like a buffer going on here, and there are some things in the buffer, and then there's also like, yeah, so it's like that. And then the server says, okay, I need something. And so it goes in and it grabs that one, and then it uses that to process. So, and then on the next tick, it will grab that one, and then like by then it'll be repopulated with new new guys. So you'll always have one. And if there is an empty tick where no network events were received, then you can grab one from here, and the size will reduce, but you won't have an empty tick. So with a NPSQ, you're trading off a bit of delay for a better synchronized processing sequence. So what I mean by this is like when you use an NPSQ, what you're doing is, so yeah, you send here, and actually let me demonstrate the empty tick. So you go here, and then let's say you go here, and then you get an empty, and then you just go back to that. So with an NPSQ, and let's say you have your CPUD or your CPUD bundle, which is CB0 here, CB1, CB2, CB3. So what you're going to do is the time at which it is received doesn't have to do with the time of its processing. So what we're going to do now is think about the tick. So even though CB0 was received here, it could be like processed on this tick. It's not actually going to be processed on that tick, and perhaps not even on this tick, but maybe on the third tick. CB0 is processed, and then on the next tick, CB1 is processed. So there's clearly some delay going on, but processing CB0 only brings the buffer down. It makes it not, it's not empty. So specifically, the buffer here would contain CB0. Here it would be containing CB0, CB1. And then here it's still containing CB0, CB1 because we haven't received CB2 yet. So we process CB0 and that leaves CB1 in the buffer. And then here we receive CB2. And then the size of the buffer goes back up to 2 and it contains CB1, CB2. And then on the next tick we grab out CB1. And then on the next tick we grab out CB2. And here we extended our buffer again with CB3. So what this means pretty much is that you can eliminate the empty ticks and double ticks by doing this. There are some intricacies with how an NPSQ works and how it where it kind of levels off in terms of the buffer size. So what's interesting to me is that you would think that the buffer would either explode in size or become empty and be empty for a lot of the time. But from my experiments, it hovers around 4 states in there, and I think that's a consequence of the variance of your network. How many it will kind of gravitate towards. But either way, a NPSQ allows you to eliminate that, and that helps reduce reconciliation error by a lot. So there aren't going to be huge jumps and stutters in your client's movement when reconciliation happens. They're going to be much less frequent. Because at the end of the day, an NPSQ can still get empty. It's not making it not happen, it's reducing the probability that it happens. And it can still happen, and it will happen. And that's when you have error decay on the client. So it's if there is a reconciliation error, then figure out what it is, and then you can decay that error away so that the player doesn't see it, or add it in slowly, so it's not a sudden jump. So yeah, an NPSQ on the server is really good in terms of helping reconciliation errors be minimized. And it adds a little bit of delay, and what I've found is that that's mostly okay. Okay, and then so that's one side of it. We're also now going to just talk a little bit about entity interpolation. So that's enemies or other objects, and how we can make those firstly render at a good rate. So let's say, I don't know, server's sending you messages now. So we're going to look at it this way. So server's sending us state, and it's sending it at 60 Hertz. And of course, that's way slower than our monitor's refresh rate. So how do we deal with that? And there's an empty tick, and we'll talk about that as well. So you've probably heard of interpolation before, and that's what we do, is that we receive this one, and we receive this one, and now that we have 2, we can interpolate between the 2. And yes, this also creates a little bit of delay because we are not immediately rendering what we receive. So we get that, we don't use it until we have a new one, and then now that we have 2, we can start to interpolate between the 2 states. So that's what we have to do. And now let's talk about how empty ticks and stuff. So in the best case, of course, each time we receive a and not only that, in order to, what's interesting here is how do we know how far we are between this one and that one? Well, we know that the server ticks at like 60 hertz or whatever. So we have like a mock server clock on the client that also ticks at 60 hertz, and we can like see how far we are to the next one. Um, and that's like it's kind of like a stopwatch. We check like how close are we to the full cycle occurring, and we use that to get the interpolation value and interpolate between them at the correct rate. Because if we didn't go at the right rate, then we would be like finishing our interpolation too early and like sticking to the end, or like not getting to the end if we're going too fast. Um, so running at the same rate that the server is running is important for the updating part. And when you receive a new one, the interpolation window, which is the start and the end state, will be updated, right? So, um, in the best case, like interpolation gets to the end state, and the moment it does, there's a new state that's received, which is gonna be like over here. So this one's received, and then the interpolation window updates to be like this one, this one, and this one. And because we were at the end and we start at the start, there's no jitter in terms of our position, and then we start our interpolation again. And yes, this is a good solution, and you're always going to be behind by one state here, and that's fine. We'll get to the implications of that a little later. But let's just talk about like the interpolation process here. So this interpolation process would work so long as like there weren't empty states. Because think about what happens when there's an empty state. So on our next window we're still fine actually. So we have that one, and then we have so our state was received here. So we update our interpolation window to this. To between these two. But then on the next tick, there was no game state received from the server. And so what that means is our interpolation is going to kind of get stuck at the endpoint here, because it's like during this whole frame, there was nothing to interpolate, right? Because there wasn't well, sorry, let me say it a little bit better. So when we're at time, like, we're always interpolating between the previous state and the next one. And when the interpolation is over, i.e. we get here, and yeah, like we're not interpolating in this way, like really it's kind of offset in terms of the time that we're interpolating, so I'll make like a better drawing, I guess. So if this is like game state 1 or GS0, and this is like game state 1, and then this is like game state 2, this is like what was received. This is like game state 3. And this is game state 4. Then like between this tick and this tick, we're interpolating between GS0 and GS1. And then we're going to be interpolating from GS1 to GS2. But then we can't interpolate from from GS2 to GS3, yeah. But then like we can't start like interpolating between anything until right now when we receive GS4. And what that means is like this duration here, there was nothing to interpolate, and so most of the time, like you don't usually, like you can extrapolate your positioning, but that's also going to produce error. Fundamentally, we're trying not to use hacks. We're just trying to like make it proper, and then like if it really goes wrong, we can extrapolate. But like this is gonna what this red here is gonna look like is you're gonna have like like a ball or like a person jumping, they're gonna be jumping and falling and then just like stop for like a frame or two and then just like continue moving. And that just looks horrible. So it just makes it look jittery and like bad pretty much. And so what we can understand here is that the interpolation is also suffering in the same sort of way that the reconciliation is suffering, in that like without with the raw network signal, it makes problems. And so what we can also do is put an NPSQ on this. And so what this means is that like the interpolation system is also just a thing that like wants to grab the next state, and an NPSQ is just a thing that makes it so that the signal, or when it's time to grab it, there's always something there, and it does that at the cost of some delay. Um, so yes, all we have to do to make this interpolation system work a little better is to put a layer on top of it, which is like the NPSQ, and it just means that like you'll always be able to grab, and there will be a new state to use with a high probability. So yeah, so fundamentally, that is the whole architecture in terms of smoothing out the network. So there's an NPSQ on the server, there's an NPSQ on the client, and they're both used to reduce the producer-consumer problem, there being like an empty or more than one state that needs to be consumed. Um, and yeah, so in terms of like firing and interacting with these interpolated entities, then like when you do something on the client, like if I did an action that depended on a non-local entity that's being interpolated at this time, then when that thing happens and the next time like we send out to the server, we package along kind of the interpolation window in terms of like the ID numbers of the game states and also the t value between 0 and 1. And then on the server, we're able to do, it's called time traveling, but I just really, it is like going back in time, but you're just recreating the scene as the client saw it at that time. So that's important, because if you don't do that, then like it'll look like they fired and hit someone, but then the server says no, you actually didn't hit anyone. So this is just called like, you just pass the data to recreate the state that was visible on the client to the server, in terms of like it's not authoritative in any way, because you're just passing the ID of the two and the t value, so you're really minimizing the data. You're not like saying the player was there and that player was there. You're just like referencing data on the server. And yeah, to make it safe, you can like make the server not accept game state values that are really old, so you can't like shoot someone a long time ago, to minimize that time travel. But in general, yeah, you can use this to recreate the state. So yeah, this is pretty much all the conceptual ideas that go into like a system like this, to make it work properly. So yeah, just recapping really quick, this type of system provides a way to refresh the client's state at a rate which is as fast as like their monitor can go or their PC can go, and it actually have an effect on the game. So through bundling, that information is not just like extraneous client data, that's actually being processed on the server and used to like update your state. Then we use entity interpolation to make all of the entities look like they're moving also at that same rate, and we use NPSQs on each side to smooth everything out and reduce empty and double ticks. And also one thing that I did want to mention was, with a bundle constrained DT, the reason why you want your refresh or your update rate to be your client side update rate to be an integer multiple of the 60, which is the server's tick rate, is that the bundle constrained DT, like if you have two numbers that aren't divisible by each other, like let's say we have 6 and 14, right? So 6 plus 6 is 12, and then there's 2 over, and so the remainder is 2, right? So with the bundle constrained DT, you want to so that's like the quotient remainder theorem. So when two numbers are not divisible, that remainder is non-zero. And the reason why I'm talking about this is that the bundle constrained DT will return a remainder which is like dissimilar from the previous DTs, and so you'll have a DT of size x, size x, size x, size x, and then a DT of size like x divided by 2 or something. And what that produces is like it will make it a little bit jerky, in the sense that like your position will be updating um, more or less like evenly, and then suddenly you'll kind of have one that doesn't goes evenly. So it's recommended to use an integer multiple of the update rate of the server. I'm sure there's a way around this, but for now, that's just something I wanted to point out. Hopefully that makes sense. And yeah, that's the entire system at a high level. Obviously, like there's more to it than that in terms of like making it compile and like things that are nice to have. Like we're using like a meta program that will like automatically serialize the things that I need to be serialized so that like I don't have to write serialization functions. But yeah, in terms of architecture and making it smooth, that's all that I wanted to talk about. So that's it.